3,000 feet deep, the ocean reaches total darkness. This is the Bathypelagic zone, a hyper-extreme environment where survival requires massive biological investments. For the massive organisms that live here, finding a target is a nearly impossible engineering problem. You have to locate and neutralize an opponent while fighting through zero visibility and crushing hydrostatic pressure. This legendary clash offers a masterclass in opposing evolutionary strategies. It pits the active mammalian tracking of a whale against the reactive, specialized stealth of a cephalopod. Historically, our understanding of these battles came from scarred carcasses and maritime lore, leaving the specifics of the actual engagement to the imagination. Newly acquired 2026 satellite tagging data finally shifts this topic into an observable, data-driven biological case study. The sperm whale is the heavy hitter of the deep, representing a high-energy, active offensive system. Its rival, the giant squid, is a master of reactive stealth, with a body specialized for grappling and rapid evasion. Both creatures are constrained by the same baseline environmental metrics, 0% light and the crushing weight of the deep ocean. These weapons come with a heavy metabolic cost. Biological resource allocation means every defensive or offensive maneuver drains a strictly finite energy budget. Survival depends on which evolutionary loadout manages that energy budget most efficiently under pressure. Looking at the whale's hunt sequence, the detection phase begins with its primary weapon, biological sonar. This functions like a long-range organic radar, tracking soft prey in complete darkness. But the trade-off is this sonar acts as an active beacon, broadcasting the whale's location to sensitive prey long before it gets within striking distance. As it closes in, the whale deploys a second offensive tool, powerful acoustic sonic booms. This focused shockwave is designed to stun the squid's nervous system, leaving it momentarily defenseless. Generating these strikes requires a massive metabolic input, drawing heavily from internal reserves. The ultimate constraint is oxygen. It has a strict 90-minute limit to dive, find a target, win, and return. This offensive strategy is a literal race against the clock, where the whale trades finite oxygen for sensory dominance. The squid's loadout focuses on defense, beginning with a massive investment in its basketball-sized eyes. These massive receptors are tuned to catch the faintest flickers of bioluminescent movement in the abyss. While sensitive, these large organs represent a major vulnerability point if the encounter turns into a physical struggle. For protection, the squid relies on advanced camouflage and the deployment of dense ink clouds. These achieve instant visual disruption, allowing the squid to disappear against the black backdrop of the deep sea. But this strategy has a fatal flaw. Visual camouflage and ink clouds are completely useless against a predator using acoustic sonar to track its targets. Because its primary stealth is entirely bypassed, the squid has to rely on rapid, short-burst jet propulsion rather than trying to hide. When the distance finally closes, we enter the strike phase. This is where physical grappling begins in earnest. The squid's main defensive input is its array of specialized, serrated suction cups. These summations rate across the whale's skin, leaving behind the deep, circular battle scars that first revealed this rivalry to us. To use these cups, the squid has to stay in the whale's crush zone, right within reach of its massive jaws. The massive whale counters this grappling defense by using its 80-ton mass to deliver high-impact, devastating blunt force strikes. Fighting through the squid's grappling secures the calories, but it burns the whale's last critical reserves of oxygen. If the initial strike doesn't end the fight, the whale has to choose between aborting the hunt or risking drowning. This encounter is governed by the lopsided rules of energy economics. We map these strategies onto a quadrant chart. One axis tracks burst speed versus endurance. The other compares passive detection to active tracking. The sperm whale occupies the active endurance quadrant, dominating long-game engagements. The giant squid sits in passive burst, surviving by breaking contact quickly. The winner is determined by the situation. The whale dominates a prolonged hunt, but the squid wins if it can outlast the whale's oxygen timer. These high-stakes events leave a permanent mark on the environment, often appearing as massive carcasses that wash up on our shores. This predatory tension is a crucial regulatory mechanism that helps maintain the delicate balance of the deep-sea ecosystem. The latest submersibles are finally giving us a look at this environment in its natural state. which is currently rewriting our understanding of cephalopod intelligence. You can help preserve these mysterious environments by supporting marine conservation efforts that protect the deep ocean from disruption. Understanding the deep sea requires moving past the mythology of monsters to appreciate the brutal mathematics of evolutionary survival.